Hey everyone, welcome to The Explainer. So, today we're diving into what is honestly a 150-year-old scientific cold case. Literally a cold case. We're looking at something you've probably experienced a million times, maybe even slipped on a few times yourself, but totally take for granted. I am genuinely so excited to share this with you. Here is our central question. Why exactly is ice so slippery? Think about it for a second. If you step onto a smooth sheet of glass or, a polished rock, you don't instantly go flying across it. But the second your shoe hits a patch of winter ice, bam, you're fighting gravity. What makes frozen water so incredibly unique? To really get this, we've got to plunge right into the history of this mystery, because scientists have been fiercely debating this everyday phenomenon for well over a century. Okay, let's look at this timeline. It perfectly maps out our detective story. Way back in the 1850s, Michael Faraday had this early hunch about something called a pre-melting layer. But then classical physics took over, and spoiler alert, classical physics actually got it wrong. In 1886, John Joly pitched pressure melting, and later in 1939, Bowden and Hughes argued for frictional heating. Those two ideas pretty much ruled the textbooks for 100 years. But as you'll see on the right there, starting around 2018, all the way up to recent 2025 breakthroughs, modern molecular insights have completely rewritten the rules. Section 1. The prime suspects, pressure, and friction. Let's interrogate these initial suspects. For the longest time, physics textbooks told us this case was closed thanks to two main ideas. On the left, we've got pressure melting. The thought here was that a skater's super thin blade puts intense pressure on a tiny sliver of ice. And according to thermodynamics, cranking up the pressure on ice lowers its melting point. So the idea was that you're essentially forcing the ice to melt right under the blade, creating a little puddle. Then on the right, there's frictional heating. This camp argued, well, no, it's not the pressure, it's the rubbing. The physical sliding of the skate generates heat, melts the ice, and boom, you've got a liquid film acting like a lubricant. But here's where the plot thickens. Under modern scrutiny, those classic models completely fall apart. I mean, look at these plot holes. First off, peak figure skating happens at about minus 5.5 degrees Celsius, and hockey is even colder, around minus 9 degrees. Pressure melting just cannot account for melting at temperatures that low. Plus, when you crunch the numbers, a normal human's weight isn't anywhere close to being enough to alter the melting point of ice. And as for friction, well, frictional heating requires movement first to generate the heat. So how do you slip before you even move? Actually, physicist Daniel Bohn hit the nail on the head with this quote. He said, "You only melt the ice behind you, not the ice you are actually skating on, right? Because if friction causes the melting, it totally fails to explain how we slip the exact millisecond we step onto the ice before we've even moved an inch. There just had to be something else going on here." Section 2. The twist. Modern molecular discoveries. So, this brings us to the modern era of our explainer. We're shifting away from the macroscopic world of skates and shoes straight down to the microscopic level. Remember Michael Faraday from our timeline earlier? He hypothesized this back in 1850, but we finally have the atomic force microscopes and computer simulations today to actually prove it. It's called the pre-melting layer. See, deep inside the ice, water molecules are locked up tight in a crystal lattice. But right at the surface, they don't have as many neighbors to bond with. This gives them this incredible freedom to move around, even when it's freezing cold outside. Just look at this molecular view. Those weakly bonded surface molecules aren't just sitting there vibrating. They're literally tumbling and rolling over the surface. The ice surface isn't static at all. It is highly dynamic. To make this a bit easier to visualize, researchers compared the ice surface to a floor filled with little balls. I mean, imagine trying to walk across a hardwood floor that's just completely covered in loose marbles. Because the molecules on the surface of the ice are so mobile and constantly rolling around like that, finding traction is pretty much physically impossible. You slip instantly, and it has absolutely nothing to do with pressure or friction. Now, check out how temperature affects this. As it gets warmer, the mean square displacement, which is basically just a fancy way of saying how far and fast these molecules are moving, rapidly accelerates. You can see the lines getting much steeper as we move up toward minus 28 degrees. And researchers actually found that this mobility peaks perfectly right around minus 7 degrees Celsius. That rapid movement creates the absolute perfect, low-friction environment for sliding. And honestly, it is no coincidence that minus 7 is exactly the temperature most indoor skating rinks keep their eyes at. Crazy, right? Section 3. Viscous water and crushed ice. Okay, let's compare the old textbook theories with a massive 2019 breakthrough from the CNRS in France, because this changes the game entirely. It turns out, even when a liquid layer does form from sliding, it is nothing like what we originally thought. The old idea assumed it was just a simple, thin layer of pure meltwater. But pure liquid water is actually a pretty terrible lubricant. The new discovery? This layer is super complex. It's not pure water, it's a mix of crushed ice and water. And instead of being thin and watery, it acts way more like a highly viscous oil.
I absolutely love the analogy the researchers came up with for this. They said the surface underneath a sliding skate is less like a puddle of water and more like a microscopic snow cone. It's this weird, mixed, viscoelastic state of crushed ice and liquid that gives ice that incredibly slick, lubricating property.
And you can see this in action right here. These are images of a manual scratch made on the ice surface. Look at what happens over just 7 minutes. Without any outside help at all, the extreme mobility of those surface molecules allows them to flow right into the defect and rapidly heal that deep scratch. The ice literally smooths itself out, which is a huge reason why it stays so remarkably low friction.
Section 4. The ongoing investigation. Amorphization. But hey, science never sleeps, right? Just when we thought we had this whole thing figured out with rolling molecules and viscous snow cones, a 2025 breakthrough study threw a curveball. They introduced this concept called amorphization. Basically, when something slides across ice, especially at extremely cold temperatures where melting really shouldn't even be possible, that physical sliding breaks the actual bonds between the water molecules. It creates these tiny microscopic welds that snap, totally disrupting the neat, ordered crystal lattice, leaving behind a chaotic, amorphous layer. So it's not melting the ice, it's structurally shattering the surface at an atomic level to make it slippery.
So, bringing it all together, this is the new modern paradigm of slippery ice that has finally dethroned those old pressure and friction myths. 1, we've got highly mobile, rolling molecules acting like a floor full of loose marbles. 2, when a layer does form, it's actually a viscous, lubricating snow cone mix of water and crushed ice. And 3, the physical act of sliding triggers amorphization, mechanically breaking down the ice's crystal lattice. These 3 mechanisms all work together, depending on the exact temperature and speed, to give you that effortless glide.
Which leaves us with one final thought. We really have come an incredibly long way since the 1850s, peeling back layers of physics, chemistry, and molecular dynamics. But, with highly mobile molecules, viscoelastic snow cone layers, and atomic amorphization all intertwining like this, will we ever consider this cold case fully closed? It just goes to show you that even the most mundane, everyday things, like slipping on a frozen sidewalk, are hiding universes of magnificent complexity. Thanks so much for joining me on this explainer. Keep asking questions.